Hey everybody, I'm going to go over the 9.1 notes, and I found an old file where I had something called quick notes. So it was really the section of the textbook, but shorter versions. And I have this for all of chapter 9. So chapter 9 is hypothesis testing. You probably, if you had AP Bio or some science classes, I know you do the scientific method. This is kind of similar in the sense that you start off with some null and some alternative hypothesis. And then you're really just doing a test to see, well, is it true? For us, we're going to do a statistical test and see, is the probability we calculate unusual? And there's a couple ways you can see this. So in general, the null hypothesis, this is what is known to be true. So coming into a situation, this is what we think is true. It's what we're testing. So it's either going to be a known population proportion or a known population mean. So our null hypotheses will either look like, for proportions, it'll be P is known to be some value, so some decimal. Or for means, our null hypothesis will be the mean, the population mean, or mu, is known to be some value. Okay, and these values will be given in the problem. The alternative is the question, what is it asking you to test? And that's going to depend on the wording. So the wording, if they say we want to test if the mean has decreased, then you would be doing an alternative with a less than. So this is if you're thinking the new parameter is actually less than what it's known to be. And again, this will either be a proportion or a mean. So for example, I'll kind of go every other here. If this was a proportion, your alternative is going to be, well, is that proportion actually less? And you'll see the wording in the problem, less than whatever this number is. Let me just give it a hashtag. Let's see. The number sign. So it's the same number. Is it actually less? We could also say, is it actually greater? And I'll use mean for this one. Okay, these parameters are going to depend on the problem. So maybe you're asked, well, what's the probability the mean is actually greater than what it's known to be? And it's known to be this number according to the null. And then finally, they could say the word different. This is almost 100% of the time you'll see the word different if it's an unequal to. Or what's the probability it's different than what it's known to be? And then your alternative, you would use an unequal to. We'll go back to proportions. What's the alternative here is the proportion's actually not equal to what it's known to be in the null. And then before I can't really make any space here, but if you think about when we calculate probabilities with these symbols, if it's a less than symbol, you should already be thinking normal here. Like for this probability, or in this kind of a hypothesis test, we're going to end up having a normal curve, and we're going to have that true parameter in the middle, and we're going to get some value. And if it's less, remember our shading is going to be to the left. So for a less than, we're going to end up having a normal curve. We'll have conditions, of course, but this normal curve will be looking for a left tail of the normal curve. If it's greater, we're going to end up having the population parameter in the middle and then some sample statistic we base it off of, and greater we shade to the right. So these are the values. We're going to calculate these probabilities and these tails. Now what's kind of new for us, we've seen a few of these this year. If it's unequal to, that means both tails. It's called a two-tailed test. So here's my parameter in the middle, so here it would be P. But I calculated some P hats, and I want to know what's the probability those P hats occurred out here. So these shaded areas are the probabilities we're going to collect here, or find. And then they have a special name. So these probabilities are called a p-value, P for probability. So we're looking for the probability that we're going against the null hypothesis. So this is the probability of the alternative happening, so to speak. Or what is this area in these tails? Okay, so these blue shaded areas are all p-values. For the first two, these p-values are from one tail, as you can see in my picture, and from the last instance with the not equal to, we're going to find probabilities in two tails. Small p-values are evidence against the null. Okay, so the smaller these blue shaded regions, the less likely they're to occur. So if the null is true and you get some small probability, well, that's shocking evidence against the null hypothesis. So small p-values are going to lead us to reject the null hypothesis. Large p-values, they don't give us evidence against the null hypothesis, because the bigger these shaded areas are, the more likely they are. And you'll see this when you calculate these values. The bigger, the better. The bigger, the more likely it is to be from the null. So small p-values, I guess I can just say small p-values, just focus, give you evidence against the null. That's a little 0. Large p-values fail to give you evidence against the null hypothesis. And again, it's because these numbers are less likely for small p-values and more likely for large. And then I just listening to a broadcast right now, and I heard the word statistically significant. So when we calculate these p-values are considered statistically significant if they're unusual enough to go against the null. So if we get a small p-value, so to be statistically significant, you have a very small p-value. And we used some numbers in the past. So common gauges of this are if you get a p-value of 0.025 or less. That's a common one. That's 2.5%. Sometimes we do 0.05. That's 5% of the time or less. And a lot of times usually the problem will tell you a significance level. Well, how small does it have to be unusual? And then even sometimes they go to 0.1 or less. But the first two are the main ones. But again, notice those decimals, if you're less than 0.05 or you're less than 0.025, you're way out in the tails of those normal curves. So these would all be examples of some statistically significant results. If something is statistically significant, so if the sample is unlikely, that means a small p-value, we're going to say, we're going to reject the null hypothesis. So if we get a small p-value or very unlikely probability given the null is true, we reject the null. Otherwise, if we get a high probability or a large p-value, we're going to fail to reject the null hypothesis, meaning it's probably still true. We never accept, never use the words accept, because we're going to base it off of some sample value. And it is possible to kind of get a sample value that wouldn't give us evidence really to really accept. So we're just going to say fail to reject. So never accept, we're just going to fail to reject it if we get a large p-value. I just kind of mentioned this a little bit earlier with my examples. There's no set rule for how small your p-value needs to be. Usually we'll be given some significance level, and they use the variable alpha. So significance level, you'll see it sometimes in problems. They might even say the word alpha. Alpha is a Greek letter. It looks like a fish. So we'll be given some alpha level or some significance level, and that's the basis that we're going to make our decision whether we reject or fail to reject. And again, usually these alphas are going to be one of these three values. And the problem will tell us the basis of whether or not we're going to reject or fail to reject. So we'll be given an alpha. But if you reject, so if you get a small p-value, smaller than the alpha, so for example, let's say my alpha was 0.025 and I got a p-value of 0.001. That is a statistically significant result, meaning we decided to reject the null hypothesis. It was unusual. And if we reject the null, we can go with the alternative in context. And we'll see some examples in the 9.1 homework quiz, and I do a video on that. If it's greater than the alpha level, so if we get a large p-value, so remember, less than alpha are small. Bigger than alpha, we consider those large p-values. then we'd fail to reject, and we can't go with the alternative. All right, because we're making decisions about hypotheses, we're not always going to be correct. So there are times where you could make errors, meaning you get the sample result, you do a significance test, you make a decision, but you were wrong. So that is possible. And these are called type 1 and type 2 errors. So a type 1 error is we reject null, meaning we get a small p-value, but it's actually true. Then we made a type 1 error. So here again, we got a small p-value, so we rejected the null hypothesis, but it was actually true. We made a mistake. Okay, we got some sample value that caused us to make a mistake in our decision. That means we made a type 1 error. Versus if we make a decision we fail to reject, so we got a large p-value in our calculations, but the null was actually false, so we should have rejected it. So we failed to reject, but we should have rejected it. That's a type 2 error. And usually if we were in class, I would give you this diagram. I have them cut out to put in notes. But I like this little diagram. So here's what's true. So if the null is actually true, but we rejected it, that means we committed a type 1 error. If the null was actually false and we rejected it, that was good. We made a right decision. It was false. We said it was false. And then you can kind of go on the opposite. If the null is true and we failed to reject it, good job. We made a correct decision. Our result was correct. Versus a type 2 error is if the null was false, meaning we should have rejected it, but we didn't. That means we committed a type 2 error. And power can be a little bit confusing. I have another diagram I have to look for in my notes, but power in a significance test is the probability the test will correctly reject the null. Meaning if the null is false, you correctly reject it. It's going to be the opposite of a type 2 error. So 1 minus the probability of a type 2 error. And I have some diagrams that show that pretty well. I have to look for. And let me go through one example here. All right, here's an example where kind of explore type 1 and type 2 errors in context, because remember, context is always important. And I always write my answer, if I do an interpretation of an error, I write the general version without context, and then I add the context in. So here, a potato chip producer and its main supplier agree that each shipment of potatoes must meet certain quality standards. If the producer determines that more than 8% of the potatoes are blemished, the truck will be sent away. Otherwise, the entire truckload will be used to make potato chips. To make the decision, a supervisor will inspect a random sample of potatoes. The producer will then perform a significance test using these hypotheses. So the null here is saying we expect there to be 0.08 blemishes or 8% blemishes on these potatoes. The alternative, what we don't want, is there to be more than 8%, or what we're interested in, not necessarily we don't want. So a type 1 error here, let's go back and review what a type 1 error is. That means the null was true, but we rejected it. So here, we would have rejected this when it was true, meaning 8% of the potatoes had blemishes, but we decided that more than 8% had blemishes. A consequence of this with these potato chips is they wasted good potatoes. Let's look at the response in context here. So type 1 error would occur if the producer concludes the proportion of potatoes was greater than 8% when the actual proportion is 8%. And the consequence here, they send the truckload back, and that results in lost revenue. They're paying for more potatoes. I got 40 seconds. A type 2 error, that's when the null was false, but we failed to reject it. So we said it was true when it was actually false. So here, we said, we went with the alternative. Let me make sure I'm saying this right. Type 2 error, the null is false, but we failed to reject. So meaning we should have went with the alternative, but instead we stuck with the null. And that means, in context, that the producer didn't send the truck back because we thought there were only 8%. And there were actually more than 8% with blemishes. And that means you're making